This video is going to cover AQA A-Level Chemistry, section 1.12 Acids and Bases, specifically looking at the pH of weak acids and Ka expressions. This video is going to cover a recap of strong and weak acids, the pH scale and pH expression, a recap of calculating the pH of strong acids, Ka and pKa, both values and expressions, and calculating the pH of weak acids. Acids that completely break apart are referred to as strong acids. And here we have an equation that shows HX, which is a general formula for a strong acid, in aqueous solution, breaking completely apart to form H plus aqueous and X minus aqueous. Now we show an arrow here because it is a reaction, it's breaking completely apart, and therefore we use an arrow rather than an equilibrium sign. Those acids that only partially dissociate are known as weak acids. And these molecules are able to donate protons, or H plus ions, but the tendency for them to do this is very low. So I'm going to represent the dissociation of a weak acid here by using HA instead of HX. Now the X in HX is normally referring to a halogen or a halide. In HA it's referring to the non-H plus part of the acid. So HA aqueous in a reversible reaction breaks into H plus aqueous and A minus aqueous. We'd end up having quite a lot of HA in the solution and not very much H plus and A minus. And it is reversible, so this would change depending on the temperature and other factors. Now carboxylic acids, for example ethanoic acid, are weak acids. So if we look at ethanoic acid, we've got CH3COOH, and it is the H on the OH that is lost. And it would form, which should be a reversible reaction, it would form the ethanoate ion, which is CH3COO minus, and an H plus, all in aqueous solution. Now here we have the pH scale, which is something that should be fairly familiar already. And pH is a measurement of the concentration of hydrogen ions present in aqueous solution, which you've probably already looked at. The pH value of a solution can be calculated using the following expression. pH is equal to negative log to the base 10 of the concentration of H plus aqueous ions. Now a log base 10 means that we have 10 to the power of X somewhere in the system that we're looking at. For pH, what it means is that between each pH value we have a times 10 factor. Now pH is a direct measurement of the concentration of H plus in a solution, as we've said, concentration of hydrogen ions. And what we've got here is between pH 1 and pH 2, pH 1 is 10 times bigger than pH 2, pH 3 is 10 times bigger than pH 4 in terms of H plus. So we have high concentration of H plus at the left hand side and we have low at the right hand side. Now this might seem a bit backwards, high H plus but low pH value, and that's where the negative comes in. So this is an inverse log scale. Now we can do the reverse, we can take the pH and work out what the concentration of H plus is. So this is the opposite process, you do need to know both of those. So now looking at the pH of strong acids. As strong acids fully dissociate, calculating the pH of these solutions is fairly straightforward. So for example, calculate the pH of a 0.5 molar solution of HCl. If we take HCl, it will dissociate into H plus and Cl minus. I'm not worrying about state symbols here. Every HCl produces one H plus and one Cl minus. Now this is because HCl is a monoprotic acid. Now monoprotic means that 1 mole of the acid provides 1 mole of H plus. monoprotic. We can get diprotic and triprotic as well, but we're talking about 1 mole of acid giving 1 mole of H+. Now, because we've got 1 mole of each, if we had a decimeter cubed of this solution, of the 0.5 molar solution, there would be 0.5 moles of HCl, which would break into 0.5 moles of H+ and 0.5 moles of Cl-. Therefore, the concentrations will also be equal if we're in the solution. So for a monoprotic strong acid, the concentration of the acid is equal to the concentration of H+. That is only the case for strong acids, and only for monoprotic acids. We'll look at diprotic later. So how do we go about calculating this? Well, if HCl concentration is equal to H+ concentration, then we know that the H+ concentration is 5 moles per decimeter cubed. And we can go straight into the pH expression. pH is minus log to the base 10 of the concentration of H+, which will be minus log of 0.5 in this case, and the answer will be 0.30. Now, pH is always quoted to 2 decimal places. That's a little rule that you need to remember. You'll lose marks in the exam if you don't do that. To look at a second example for the pH of strong acids, calculate the concentration of a solution of H2SO4 with a pH of 1.2. Now, for this one, we've been given the pH and we're being asked to calculate the concentration of the solution. Now, the solution will be concentration of H2SO4 that we're looking for here. We can state that pH is equal to minus log to the base 10 concentration of H+. And also, we can therefore state that the concentration of H+ is 10 to the negative pH. So we can go straight into working out what the concentration of H+ is by doing 10 to the negative pH, which I've already written, don't need to do that again. So 10 to the minus 1.20, which is 0.0631 rounded to 3 significant figures. Then what we have to think about is that the concentration of H+ is not equal to the concentration of H2SO4, because H2SO4 has 2 H pluses for every SO42 minus. This is referred to as a diprotic acid. It's providing 2 moles of H plus for every 1 mole of acid. So looking at the concentration of H2SO4 to H plus, we've actually got a ratio here of 2 to 1. So however much of the H plus we have, we need to divide that by 2. So we take 0.0361, we divide that by 2, and that will give us the concentration of the H2SO4, which if I put it into my calculator is 0.0316 moles per decimeter cubed, again to 3 significant figures, which is always a safe bet when you're doing calculations. So as always, it's time for you to have a go. Task 1, calculate the following. 1, the pH of a 0.1 mole per decimeter cube solution of HNO3. Number 2, calculate the pH of a 3 mole per decimeter cube solution of H2SO4. And number 3, calculate the concentration of a solution of phosphoric acid, H3PO4, with a pH of 0.9. Pause the video and the answers will follow. Okay, so the answers for task 1. If you look at question 1, this was asking us to calculate the pH of a 0.1 molar solution of HNO3. Now we do have to think through the chemicals and just think about what we've got. This is a monoprotic acid. So that tells us that the concentration of H plus is going to be equal to the concentration of HNO3 because it's a 1-to-1 ratio. pH is equal to the inverse log to the base 10 of H plus aqueous. And because we know that H plus concentration is equal to the concentration of the acid in this case, we can go straight into putting in the concentration of the acid. So negative log of 0.1, and that will come out to be pH of 1.00. Now remember, that must always be 2 decimal places because it's a pH, and pH is always quoted to 2 dP. We also just need to consider, is this a sensible pH for nitric acid, a strong acid? And a pH of 1 is absolutely fine. Question number 2, calculate the pH of a 3 molar solution of H2SO4. Now H2SO4 is diprotic. We have 2 hydrogen ions for every H2SO4 molecule. So although pH again is minus log of the concentration of aqueous, we don't need to put the 10 every time. We do need to think about what that concentration of H plus will be. And the concentration is going to be 2 lots or twice the concentration of the acid because of there being 2 H pluses for every H2SO4. So the concentration of H plus is actually 6 moles per decimeter cubed here. So minus log of 6, we put that into the calculator, that gives us a pH of minus 0.78, again to 2 decimal places. Now that might seem a bit strange that we have a negative, because most people think that pH goes from 1 to 14. In actual fact, pH goes from approximately 0 to 14, and it can be ever so slightly less than 0 and ever so slightly more than 14. So it gives us a really good ballpark to aim for, 0 to 14. If you got 20, you'd be definitely wrong, but it can be just slightly negative and it can be just slightly more than 14. And finally, for task 1, question number 3, calculate the concentration of a solution of phosphoric acid, H3PO4, with a pH of 0.90. Now, it is worth just pointing out at this point that phosphoric acid is not technically a strong acid. It is actually considered to be a weak acid, but for this question, we'll just consider it to be a strong acid because it is good to have an example of a triprotic acid. So we know that pH is equal to the inverse log to the base 10 of the concentration of H+. But we've been given pH, so we need to rearrange that equation, and therefore we need to write down that H+ concentration is equal to 10 to the negative pH. So we can work out the concentration of H+, 10 to the minus 0.90. If we put that into a calculator, we get an answer to 3 sig fig of 0.126 moles per decimeter cubed. Now the question's not asking for the concentration of H+, it's asking for the concentration of H3PO4. Now in H3PO4 there are 3 H pluses for every H3PO4. So we have a ratio of, in this case, 1 to 3. And that means that the concentration of H3PO4 is equal to the concentration of H plus divided by 3. So 0.126 divided by 3, if we put that into our calculator, gives us an answer of 0.0420 moles per decimeter cubed. So now that we've got a bit of an understanding or a reminder of the calculation of pH of strong acids, we need to think about the pH of weak acids. As weak acids only partially dissociate, the concentration of H plus ions won't be equal to the concentration of the acid itself. This means that we can't use the pH expression straight away when given a concentration of an acid. If we were asked for the pH of 0.5 mol per decimeter cubed ethanoic acid, the concentration of H plus won't be 0.5 moles per decimeter cubed. In order to calculate the pH of weak acids, we need another expression that we use before we can calculate pH using the pH expression. As the dissociation of weak acids is reversible, these systems reach an equilibrium, and so the expression used is related to Kc, the equilibrium constant for concentration. Now I am just going to add a little side note here that actually it's not directly related to Kc. We can use Kc to help us understand where this new expression comes from, but if you were to look at this at a higher level, there's actually a lot more to it than that. This is a simplification. So I want you to just have a quick think. What would the expression for Kc be for the dissociation of ethanoic acid in aqueous solution? So that is the expression for Kc. Now, if we look at the equation for the process, ethanoic acid is CH3COOH, and in aqueous solution, that would be interacting with water. It is reversible, so what would happen? Well, the ethanoic acid is going to act as an acid and donate an H plus to the water, and we end up with the ethanoate ion and the hydroxonium ion being formed. Now we could put state symbols in here, aqueous, liquid, aqueous, aqueous, but I'm going to leave it at that for now. Kc would be the concentration of the products, so in this case the ethanoate ion, times by the concentration of H+, all divided by the concentration of the reactants, in this case ethanoic acid and water. Now, in an aqueous solution, the concentration of water is huge. And if we were to compare the concentration of the water to the concentration of the ions, the concentration of the water would be massive. The ratio would really be tipped really far towards the water. And in actual fact, we can consider the concentration of H2O to actually be constant because it is so big in comparison to everything else. And so what we can do is we can therefore do the normal science thing of neglect the concentration of H2O. We can say it's so big in comparison that we can assume that it is constant and we can neglect it from the expression. Now what we mean by that is cancel it out. And I've just realised I've actually missed out. That should be H3O plus on the top of that expression there. I've confused it for everybody, but just let me correct that quickly. So H3O plus on the top. Many apologies. So going back to this, if we neglect water from the expression and we cancel water out on the bottom of the expression and also cancel it out on the top, leaving us with H plus, this gives us a new expression with the ethanoate ion and H plus on the top, all divided by the concentration of the ethanoic acid on the bottom. Now this expression is known as Ka, which is the acid dissociation constant. And as I said, it's because water is such a large concentration in comparison to everything else. So looking at the Kc expression in just a bit more detail, we can look at this generally for the dissociation of weak acids by taking the expression we talked about at the very beginning, or the equation we talked about at the start of the video, of HA aqueous being in equilibrium with H plus aqueous and A minus aqueous. Now, at equilibrium for weak acids, all three of those species would be present. How much you have depends on the actual relative strength of the weak acid, A stronger weak acid will be more tipped to the right hand side and we'd have more H pluses, but a weaker acid would be favouring the left hand side with more HA. So taking this equation, we can write a general expression for Ka. This Ka expression would be the concentration of the H plus and A minus on the top divided by the concentration of the HA on the bottom. So Ka always follows this format, and this is the general expression for Ka. So looking at task 2 next then, write Ka expressions for the following and state the units in each case. So the first one, CH3CH2 COOH aqueous in equilibrium with CH3CH2 COO minus and H plus. Number 2, the dissociation of butanoic acid. And number 3, HCOOH aqueous plus H2O in equilibrium with HCOO minus and H3O plus. As always, pause the video and then mark your answers afterwards. So moving on to the answers for task 2. The first question was CH3CH2 COOH, which is actually propanoic acid, in equilibrium with CH3CH2 COO minus, or the propanoate ion, and an H plus. So the Ka expression here is going to be the products of this dissociation, which is the propanoate ion, times by the H plus. Both of those are concentrations, all divided by the concentration of the propanoic acid itself. Now looking at units for this, we've got two concentration terms on the top, and we have one concentration term on the bottom. So one on the top cancels out one on the bottom, and therefore our unit for Ka is mole per decimeter cubed. Question 2, we're looking for the dissociation of butanoic acid. So we first need to think about what that is. Well, dissociation of butanoic acid, we write out butanoic acid first. CH3CH2CH2COOH is going to dissociate in a reversible reaction into the butanoate ion, as written there, and an H plus. So the Ka expression will be the butanoate ion, which is on the right hand side. Make sure you put the minus, times by the H plus, all divided by the concentration of butanoic acid itself. Just making sure we've got 4 carbons and everything there. Now, again, looking at the units, we have 2 concentration terms on the top, and we have 1 on the bottom. So 1 on the bottom cancels out 1 on the top, and we end up with unit of moles per decimeter cubed again. That is always the concentration of Ka for these monoprotic weak acids, moles per decimeter cubed. And on to question number 3. Here we have the dissociation of methanoic acid. Strange little compound, I always think, if we were to draw it out. That is the ethanoic acid. Now, in this question, we've actually got the H2O included, and we need to remember that the H2O is neglected when we look at Ka, so we use H plus instead of the H3O plus and ignore the water. So the Ka is going to be the concentration of the methanoate ion times by H plus concentration, all divided by the concentration of the methanoic acid, and again the unit would be moles per decimeter cubed because we have 2 concentrations on the top and 1 on the bottom. So moving on to looking at Ka values before we start looking at calculations involving Ka. Kas cover a massive range of values, and I've got a table here where I can show you some of the values just for a few examples. Now we've got strong acid hydrochloric acid at the very top, And you can see here that the value given is just large. The dissociation is well, we say that it completely dissociates, which means that we've got the bottom of the fraction, technically the concentration of HCl molecules would be 0. So actually infinitely large, you could consider that. As we go down the list, we get to have weaker acids to the point where we get to water, which is technically not an acid or a base. It's amphoteric, it can act as either. And we can see here that we have a very tiny number, that it's 10 to the minus 16. So we do have this huge range of Ka values. So in order to give us more usable numbers, we can express Ka as pKa instead. And this is exactly the same as when we express concentrations of H+ as pH. Instead of having loads of standard form data with very large and very small numbers, we can use the exact same expression for pH, but exchange H+ for Ka. And this gives us just a sort of an easier list of numbers to look at when you're looking at a data table. In the same way that we can turn H+ into pH and pH into H+, we can have the opposite of this expression, and Ka is equal to 10 to the minus pKa. In an exam at A-level, the only reason they normally would give you a pKa is so that they are giving an extra mark. If they get to the end of a paper and realise that they're a mark lower than they should be for the total of the paper, if they've given a Ka value, you might find they give you a pKa value, and then there's a mark for converting it to Ka. But it's done in exactly the same way as you do for pH. Now, have a look at the list and then think about the Ka expressions. And what do you think the link is between the strength of an acid and its value of Ka? So we're talking about numerical here. What's the trend? Well, the stronger the acid, the greater the dissociation of the acid, and therefore the higher the value of Ka. I mentioned this previously on the last slide. If we have a greater degree of dissociation, we have a larger fraction on the top of the Ka expression if we think about the fact that Ka is H+ times A- divided by Ha. A stronger acid is going to be favouring the right-hand side of the equilibrium, and so it will be the top of the fraction for Ka that gets larger, and therefore Ka is larger as well. So now we're going to have a look at calculating pH for weak acids, and we're going to have a look at an example. Calculate the pH of a solution of ethanoic acid of concentration 0.5 mole per decimeter cubed with a Ka of 1.76 times 10 to the minus 5 moles per decimeter cubed. So I've just used a little bit of exam technique there, just making sure that I know what I'm looking for, the pH of the ethanoic acid. We've been given the concentration of the ethanoic acid, which will be the concentration of the CH3COOH itself. Okay, so this is prior to dissociation, so this is assuming no dissociation there. And then the Ka they've given to us as well. Now, they've given us a Ka expression, so the sensible thing first of all is to write down the Ka expression. On the top, we have the ethanoate ion. Apologies, I wrote ethanoic acid. So we have the ethanoate ion and the H+. So that is the dissociated acid on the top. And on the bottom, we have the concentration of CH3COOH, the ethanoic acid itself. So that value on the bottom would be 0.5. We've been given the Ka, we've been given the ethanoic acid concentration, and we want to know the H+, because pH is minus log H+ concentration. So to calculate the pH, which is what the question is asking for, we need the concentration of H+. What we don't know, however, is we don't know the concentration of ethanoate ions. However, because this is a monoprotic acid, the concentration of H+ is going to be equal to the concentration of the ethanoate ions. Every ethanoic acid molecule that breaks up does so equally. And one ethanoic acid will produce one ethanoate ion and one H+. So although the ethanoic acid is not equal to the ethanoate, the H+ and the ethanoate are always equal. And that is something that is true for weak acids whenever they're in solution on their own with water. As long as it's just a weak acid in water with nothing else interacting, that will always be true. As soon as you start adding any other chemicals, for example bases that will react or salts that interact to form something called a buffer, which is later in the topic, this bit I've highlighted in yellow is not true. But as long as it is just a solution of a weak acid, then H plus always equals A minus. Now, if we take that into account then, if H plus is equal to ethanoate in terms of its concentration, we can simplify the top of this Ka expression, just as part of our working, to be the concentration of H plus squared, because those two values will be the same. And now if we look, we've got the Ka given in the question, the concentration of the ethanoic acid given in the question, and we want to calculate H plus. So we now do have everything that we need for this. Now I'm going to rearrange this calculation, this expression, to give us H plus. And first of all, H plus squared is going to be equal to Ka times the concentration of the ethanoic acid. So what I've done there is I've times both sides of the expression by the concentration of ethanoic acid, and it cancels out on the right. And then I'm also going to square root both sides, which will have the job of getting rid of the squared. At which point I put in the values, 1.76 times 10 to the minus 5 times 0.5, all square rooted, which gives us an H plus of 3 times 10 to the minus 3 moles per decimeter cubed. pH is equal to minus log of H plus, which minus log 3 times 10 to the minus 3 gives us a pH of 2.53, as always to 2 decimal places. Now, first of all, that is a suitable pH because it is between 0 and 14, so we're in the right range for an answer. And then we just have to think through the chemical that we're looking at to just decide if it is a sensible answer. Ethanoic acid is a weak acid, so it is going to be less than 7, but not at the very, very low end. And also ethanoic acid is the main component in vinegar. And if you can remember some of the common substances like vinegar and lemon juice and that kind of stuff, it is really useful. A pH of between 2 and 3 is absolutely perfect for the pH of vinegar. So moving on to task 3 then. Got an exam style question for you, which I'd like you to complete. So the acid dissociation constant Ka for propanoic acid has the value of 1.35 times 10 to the minus 5 moles per decimeter cubed at 25 degrees C. A. Write a chemical equation to show propanoic acid in water. B. Give the full expression for Ka for propanoic acid. And C. Showing all working and explaining all steps, calculate the pH of a 0.117 mole per decimeter cubed solution of propanoic acid. For the final time in this video, pause and have a go at the question. So answers to task 3. A asked us to write a chemical equation to show propanoic acid in water. Now there are actually two answers you could give for this one. The first one that would be acceptable would just be to show the dissociation of the acid directly into the propanoate ion and the H+, or you could show the propanoic acid reacting with water itself to form the propanoate ion and the hydroxonium ion. Either of those would be acceptable as an answer. Next, they're asking for the full expression for Ka for propanoic acid. Now what that means is they want you to use propanoic acid and the propanoate ion. They don't just want the general H plus A minus version of the expression. Now they might not say in the question give the full expression, but if you're asked for an expression for a specific chemical, you have to give the specific Ka. So for this one, it is one that we have already written in this video, but Ka is going to be the concentration of the propanoate ion times H plus divided by the concentration of propanoic acid. And then for part C, showing all working and explaining all steps, calculate the pH of a 0.117 mole per decimeter cube solution of propanoic acid. Now I've rewritten or copied and pasted the Ka expression there for propanoic acid, just so we've got it to work with. Now, where it says showing all working, that's really important. That means rearrange before you substitute, rearrange then substitute. Very, very important to make sure that you do that and don't just stick numbers in, because if you rearrange incorrectly, you'll lose marks. Now, the explaining all steps thing is where we need to be thinking about what we can do to this expression. Now, we've been given a concentration here, and that is the concentration as before of propanoic acid. So that's the concentration of the acid itself, I should say. So it's always worth sort of like jotting things down. So we've got the concentration of the species on the bottom of this fraction. We have been given the Ka value. So we've got Ka, and we're trying to find H plus because we are calculating the pH of this solution. And remember that pH is minus log of the concentration of H plus. As we've said before, for this example, because it is weak acid in water with nothing else interacting, the concentration of H plus will equal the concentration of A minus. And this is what we mean by explaining all steps. It's because of stating H plus equals A minus that I can then simplify this expression and put H plus squared over the concentration of the propanoic acid. Now you could use the general expression using HA and A minus for this. You could put HA on the bottom there instead of writing out the full formula of propanoic acid, but just for clarity I'll leave it like that. You cannot ever write H plus squared if you're asked for an expression for Ka. This is only working. So I'm going to rearrange the expression as we did previously in the example, and we will find that Ka times the concentration of the propanoic acid, all square rooted, will be equal to H plus. So if I put the numbers in, again all square rooted, we get an H plus of 1.25 times 10 to the minus 3, which if we work out the pH, I would normally write out the full expression, but I have already written up the top here, so I'll just put the number in. Anyway, we get a pH of 2.90, as always, to 2 dP. And again, is that a sensible pH for a weak acid? Around 3 is absolutely perfect. So if you got that, well done. And if you have any questions, let me know.